Hello, this is FlippedHarber for Physics. In this video we'll talk about velocity and position with acceleration. Now basically this video is going to be about how some equations were created or derived that will let us calculate velocity and position when we have constant acceleration. The outline for the video, we'll talk about what acceleration is. We'll talk about how to find velocity when there's acceleration. We'll talk about finding displacement from a velocity time graph. And then we'll talk about an equation that lets us find position or displacement with average acceleration. And then we'll end by looking at another very useful equation when we don't actually know the time involved with the acceleration. Now, first of all, you should already know that acceleration is equal to the change in velocity over the change in time. So that's Vf minus Vi divided by time final minus time initial. Now, a lot of times we don't really talk about time final or time initial. We just talk about the time that's elapsed. So quite often you'll see this equation is just A equals Vf minus Vi over t, where that time is a time interval instead of a final and initial time. Alright, so if we want to find velocity with acceleration, that is, we want to find the final velocity of an object, basically we can take that equation and solve for v sub f. Now this is a very useful equation. We see it quite often in this form, but there's a couple other variables we might want to solve for. So if we shift things around, we've got the equation for v initial, that is, how fast was the object going. And then finally, solving it for time, we just take our change in velocity and divide by the acceleration. We can find out how long it took that object to speed up or slow down. Alright, now let's talk about finding displacement from a velocity time graph. Now remember, your velocity time graphs should always be in red. And that's a useful way for us to distinguish velocity time graphs in the book also. They stick with that convention. So here we see a velocity versus time graph. There's technically two velocity versus time graphs here, but I want to talk about the upper one where the object is traveling at a constant 10 meters per second. Now, the area under this nice horizontal line we could just find by using our area equation for a rectangle. We take our height and multiply by our base. Now, you might be wondering, why in the world are we talking about area? Let's hold off to that question for a couple seconds, and I'll explain why we're finding the area. So, if we take our height, that is our velocity, and multiply by our base, that's a time. So hey, there we go. When you take the area for this rectangle on the screen, you're actually finding the displacement. So that's why we're talking about the area under this graph. Whenever you find the area under a velocity time graph, what you're finding is the displacement of the object. How far has it traveled? And this is true no matter how complicated the graph is. If you can find the area under the graph, that is between the graph and the horizontal time axis, you are finding the displacement of the object. This is true when it's a positive velocity. This is true when it's a negative velocity. It's true when it's zero. Look, that bottom line is a velocity time graph for an object that's not moving. If it's not moving, it's not going to cover any displacement. The area under that line is zero. Now, if we stick with this idea that the area under a velocity time graph is displacement, it's a great way to develop another equation for us. So let's take the area under this velocity time graph. Now, it's a triangle, right? We've got a triangle made by this angled line, the time axis, and then a vertical line at 5 seconds. So if I want to find the area of this triangle, I need to use my triangle area equation, 1/2 base times height. Well, our base is the time, 0 to 5 seconds. Our height for this triangle is that vertical side of the triangle. It's from 0 to 25 meters per second. It's our velocity at the end of that triangle. So our displacement is equal to 1/2 v final times time. Well, what if we don't know our final velocity though? Well, there's a way to find our final velocity, and that's to take our acceleration times time. So that v final, that 25 meters per second, is actually equal to the acceleration of this object times the time. Well, hey, let's just go ahead and multiply a little bit and get displacement equals 1/2 acceleration times time squared. Now that's a very useful equation. It tells us how far an object will go when it starts at rest, that is 0 meters per second. It has a known acceleration for a known amount of time. That's a very useful equation. But we can make it even better. If we add in an expression about how far it would go with an initial velocity, that is a vi, and we can even add in, well, what if its initial displacement was not 0? Quite often we take our initial displacement to be 0, but it doesn't have to be. We get a total complete equation for final displacement when we know an initial displacement, an initial velocity, so this object doesn't have to be starting from rest, and an acceleration and a time. This is a very, very useful equation. Yes, it's got a lot of variables in it. It's got a lot of stuff to plug in. But fortunately, a lot of times things are 0 for us, and whenever the initial displacement is 0, that first term goes away. Whenever the initial velocity is 0, that second term will go away also. So looking at all the different ways that this can be solved, we could solve this equation for the initial displacement. We could solve this equation for the initial velocity. We could solve this equation for the acceleration. Heck, we could even solve this equation for time. And if you're looking at that last equation going, man, that really looks familiar, well, you know what? I actually made it by using the quadratic formula. Now, these would all be great to write on a sheet and keep handy so that you can refer back to it. Okay, this should really end up in your test booklet. Okay, this is one equation solved 5 different ways for the 5 different variables. All right, that one other equation. Okay, this is a very useful equation when time is not known. If you're sitting there and they're asking for a final velocity or an initial velocity or an acceleration or even a displacement, and they don't tell you the time, this is your go-to equation. We've got Vf squared equals Vi squared plus 2 times the acceleration times the change in displacement. Quite often that change in displacement is just our final displacement. Usually that's just one number. But this is a very, very useful equation. I'm not going to bore you with how we derive it. I know you don't really care. You just want to use the equation, learn how to use it. So there it is. Make sure that you write this equation down. You're going to be using it a fair amount in class. You're going to be using it on your homework, on your tests, on your quizzes. Looking at it solved for the different variables that it could be solved for, solving it for Vi, the initial velocity, solving it for acceleration, and that last one, I solved it for the change in displacement. You've probably got the gist about we're usually using Di as 0. I leave it in there because Di does not have to be 0, but quite often Di is 0. So we're just finding the final displacement most of the time. Alright, that's it. I hope you wrote them all down. If not, you get to back up this video and write those suckers down. They can also be found in the book. A handy place to look for your equations from a chapter is back at the end of the chapter. They've always got a list of the equations. It's always under the chapter study guide. For example, chapter 3 study guide on page 79 has all of these equations. Not all solved out for the different variables like I did for you, but you can always look there and see, hey, what equation should I know from this chapter? All right, good luck. I'll see you in class, and I'll see you online.